Hello everyone. In this third video of reviewing the classic controls, I'm going to show you a lead compensator design for this system. Now this system is a little bit different than the system I used in my previous videos, and the reason for that is this system is stable and it has infinite gain margin and phase margin, and that's not what I want. So I changed it from this one to a little bit different that has a limited phase margin, still has infinite gain margin. So, but its phase margin is smaller than what I want. So it justifies adding a lead compensator to make the phase margin bigger and also to reduce the steady state error to the ramp input. And ramp input, because this system, if you look at it, is type 1. So that is the first thing we're going to do, and the design is in the frequency domain. And the second thing, I am going to design a PID controller for that original system to put the settling time below some limit, overshoot below some limit, and a steady state error to a ramp input below some limit. Okay, so we're going to do two things, both of them control design. Now one of them is a lead compensator, the other one is a PID controller, and we're going to do it theoretically and also this in this part. To make it more interesting, I'm going to show you the basically the control system designer app, which is available under apps, right? If you go here under applications for controls, you should be able to see that. So I'm going to go for that for my system, and I show you how to also do it in MATLAB. Okay, so let's get started with the first one. So if you watch my videos on the playlist control for lead compensator design in frequency domain, you remember that the lead compensator has this form. So it is Kc times the zero is at 1 over t, and the pole is at 1 over alpha t, where this alpha is less than 1. And so clearly the zero is closer to the imaginary axis than the pole, so it acts more like a derivative. So the zero is dominant. And the goal is to determine these three parameters, Kc, T, and alpha. Okay, if we can determine these three parameters to satisfy these needs, guess what? We have designed our lead compensator. So how do we do it? The first step is to make sure that we set this gain Kc such that the steady state error system is satisfied. So the first place that we go over is the last one here. Now, this system is clearly type 1, right? So you see this is like S times S plus 2. It is a type 1 system. And in a type 1 system, the error to a ramp function, the steady state error to a ramp function, if you remember, is 1 over kV. Static velocity error constant, where this kV itself is the limit of S times G of S as S goes to 0. So in the current system, it is basically 8 over 2, which is 4. And so your steady state error is going to be 1 over 4, or 0.25. So right now, your steady state error to ramp is 0.25, but I'm going to bring it down by a factor of 2.5 to make it less than 0.1. For that to happen, of course, this kV of the system, the new kV, if I call it kV prime, should be the old kV times the ratio between these two numbers. So it should be 2.5 times the old kV. Okay, so this number should be multiplied by a 2.5 to make it happen. And where does that come from? Well, in the new system, it is going to be the limit of S times what? Now your GC is going to go behind G, so your system is going to be now like this. You have your compensator, you have your plant, and then you have the closed loop, right? And h here is still 1. So here, your open loop transfer function is g times gc, because again, h is 1, so it is going to be like this when s goes to 0. Now, the original system g, this limit for it is limit of s times g is 8/4, but for gc, what's the limit? When s goes to 0 in the gc, what's the limit? It is going to be kc times 1/t divided by 1/alpha t. This alpha comes up, so this part is going to be kc times alpha, and this part is going to be 4. Okay, which is 8/2. If you want, I can write it as 8/2. And how much should that be? Because this guy is 0.1, so this one should be 10. So this new guy should be 10, and 10 is 4 times kc alpha, so kc times alpha should be 2.5. The product of these two gains, kc and alpha, should be what? 2.5. Okay, so if I multiply, as I said, this system by a 2.5, which comes from kc and alpha of the compensator, that is going to have this error condition satisfied. Now, what do we do next? So that's the first thing we found, this equation 1, kc alpha is 2.5. The next thing we do, we consider just a simple gain of 2.5 multiplied by g, and we define it as a new uncompensated system, g1, which is simply 2.5 times g, so it is going to be 20 over s times s plus 2. And now we are going to draw the Bode plot of this gain compensated but not lead compensated system. And here we determine the phase margin of this system and the gain margin of this gain compensated system. How much are they? So for that, here we go to MATLAB, although we can do it analytically as well, but that takes a lot more time. So here I'm going to do it in MATLAB. So my G here is the system, and I say G1 is 2.5 times G. So this G1, and then I do plot of Bode for G1. Okay, and I can find phase and gain margin either graphically, or I can use the command that I showed you in the past, where basically you use the command margin, and that one give you gain margin, phase crossover frequency, and gain crossover frequency. We don't need these two right now, but these two we do need. So I can get those directly from here, and you see your gain margin is infinite, but your phase margin here is about 25 degrees, right? So this one is infinite, this one is about 25 degrees, okay? If that's the case, now I have to raise this phase from 25 to something bigger than 60. Now here, to make the problem a little bit easier, let's say I just want to go with 50 instead of 60, okay? So I make this 50, and by easier I mean like, so I don't do a bunch of iterations, I just keep it a little bit lower. So let's say above 50 degrees is good for me. So I should go from 25 to 50 degrees. I need 20 extra 5 degrees to add to the system to make it happen. So the phase deficiency that I have, phi, and maximum of it from a lead, phi m, is equal to the desired phase margin, 50, minus the actual one, 25. But it is always recommended that at least add 10 extra degrees to this to be safe. Because when you add the lead compensator, it shifts the gain crossover frequency. It doesn't keep it in the same place. So here I recommend you add at least some extra 10-15 degrees just to be safe. And here I just add an extra 15 degree bonus. Just, you'll see, even with that, you might not end up with 50 degrees, okay? So the phase that I need is how much? it is about 40 degrees. I need a 40 degrees contribution from the lead compensator to get the phase margin that I want. Okay? Yes? Now, if that's the case, I can find alpha from this angle. In a lead compensator, there is a relation between alpha, the attenuation factor, and the maximum contribution phase. And that is the formula, that alpha equals 1 minus sine of this phi m divided by 1 plus sine of phi m. So now I need to say 1 minus sine 40 divided by 1 plus sine 40, and that should give me the alpha number. So let's see if I have something somewhere that I can use. Okay, so 0.217 is my alpha, and this number should definitely be less than 1. So there we go. I found my alpha. That is my alpha. And since I have alpha and I have alpha times Kc, that means I can find Kc as well. So Kc is going to be 2.5 divided by this alpha, and I can find that number as well. So here we go. So it's 11,521. There we go. So far I found two of my parameters, the attenuation factor and the gain. Okay, now what? Now you go and look at the Bode plot of this G1 that you just made and find a location in it where the magnitude of G1 is equal to 10 times log 10 of alpha. Find a place where the magnitude is equal to this number. Now, how much is that number? First, let's find it. So 10 times log 10 of this 0.217, right? It is negative 6.6364 decibel. So let's see at what frequency, this is going to be the new gain crossover frequency, at what frequency you have such decibel, negative 6.64. So here we go to this plot and we try to find negative 6.64. So it is somewhere between these two frequencies. Look, it's between 6 and 7. And the first one is negative 5.5, the next one is 8, and this one is 6.6. So it is not exactly between the two, it's closer to the 6 than to the 7. It's kind of like 1/3 way. So I would say if I want to interpolate, it's something like 6.3 or so. Now, if you want to get better results, because here it jumps big time, what you can do is you can basically generate a lot of frequencies and do the Bode plot with a lot of frequencies. Look here, when I do Bode of G1, the frequencies it generates is between 0.1 and 100, and probably it is only using maybe 20-30 frequencies. But I can make a lot more frequencies by saying a W equals log a space of from 10 to the negative 1 to 10 to the 2, 1,000 frequencies. Use 1,000 points and do Bode of G. So now it does it with a lot more points here. So now you can click on a lot finer. Look now, you see? I can move it a lot finer instead of just guessing. So now, remember, the number that I was looking for was 6.64. Let's see if I can move this magnitude to 6.64 or very close to that. There we go. Look, you see how close I am? It's between 6.38 and 6.42. So 6.4 is a good number. And this one is now going to be the place, the new gain crossover, and that is the place where you can have your maximum phase contribution. and the location, the frequency for the lead compensator at which phi, the contribution, is maximum, also has a formula, and that is 1 over t times the square root alpha. And guess what? From here, I should be able to calculate my t because alpha is known. So all I need is to calculate t. So it's going to be 1 over this number over square root alpha. So it's going to be 1 over 6.4 over square root of alpha, and that is 0.335. There we go. I found all 3 parameters of the lead compensator. So now what is my compensator is going to be? Well, let's just plug in the numbers. So Kc was 11,521 times S plus 1 over T and S plus 1 over alpha T. So I need to calculate 1 over T and 1 over alpha T. So the first one is 1 over this number, which is 2985. And the second one is 1 over this number and divided by 217, which is 13,756. So this is my compensator. If I add it right behind C in series, ideally it should satisfy all of these conditions. So let's see if it does. So what do we do now? Now we define the GC as the transfer function of. So let me put this on my second monitor so I can read off of it and put it down for you. So this guy is 11.521 times S, which is 1, and 2.985, and the other one is 1 and 13.756. So that is my compensator, lead compensator. G itself is this guy. Now I want to know if I basically multiply G by GC using a series command and get the Bode plot of that, would I get what I want? So here I say series of G and GC, right? Give me the Bode plot of this one. Do I get that 50-degree phase margin, 10 decibel gain margin? Or if you want, I can use that margin command again, right? If I don't want to read it off of this, I just go ahead and do it here. And look, your phase margin is 57 degrees, your gain margin is infinity, and that is better than what I wanted. So this one turned out to be 57 degrees. This one is still infinite. That error is definitely 0.1 the way we calculated it in a ramp response, and this is definitely a good stable system. And we can always look at the response of this system if you want, right? So we can say closed loop transfer function equals, and then we need to pass to it the feedback of series of G and GC and 1. Right? So this is my closed loop transfer function, and now for instance I can look at the step response of it or anything else. I can look at the root Lucas of it. I can look at anything that you want. There we go. Clearly you see this is stable. And I can look at the root Lucas of that, as I said, and make sure the system is stable for the numbers that it has right now. R locus. Okay, and you see everything here is on the left side of the imaginary axis, so the system is fully stable. And it gets all of the thing. You can even do the ramp response if you want, right? So you say t equals 0 with increment of 0.1 to, I don't know, 100, and then u equals t, and then y and t equals LSIM of the closed loop transfer function and u and t. get that, and then plot T and Y. So you can look at the ramp response. And if you want, you do a hold on, and then you plot T and U in a different color, so you can see the input and the output of the system next to each other. There we go. So red is the ramp, blue is the response. It's not very easy to see any difference between them unless you zoom into the plot. You can see some small differences. And if I zoom out and go to big numbers, let's say here, you see there is a gap between them, and guess how much that gap is? Look, this is 100, this is 99.9. The gap is only 0.1. And that is exactly what we wanted. We wanted the gap to be 0.1, and it is. Okay, so you see this one satisfies everything that I wanted in the system, and I did the design by the frequency domain. And 57 degrees phase margin and infinite gain margin is a very good relative stability as well. You see? So this is how you do a lead design in frequency domain. Now let me show you how to do it in MATLAB also, if you want to do that. So here you bring in the control system designer app and call it on G. Okay, so call it for the G, and then it allows you to pick a controller and then tune it manually to get the numbers that you want. So let me show you this one. There we go. You see, right now it shows your phase margin as 38. That's interesting because in MATLAB it was not necessarily the case, right? Or maybe we did it for G1. We found the phase margin for G1, not for G. Okay, so this is for G. For G, phase margin is 38, but for G1 it was 25 because the gain was adjusted. So this is G, okay? We can do it directly for G. So now what? And gain margin is infinite. So I want to raise this 38 to a bigger number, 50, 60, some angle that I want. And by the way, this is the step response and this is the root locus of the system. So you have frequency responses and time domain and S domain. So what do I do here? I go right click here and says, hey, design requirements. Okay, you can do those, but before that you need to pick a compensator. So say edit a compensator. Let's add the compensator. Now right now you don't have any compensator, but you can right click here and say add a pole 0. And then how do you want to do it? I say I want to do it with the lead compensator. And there we go. It adds a lead compensator for me, and you can set all of the initial numbers for it. So let's say, for instance, in this system, I want a gain of 2.5, but I don't know where to put the pole and the 0. So right now I just put them at -1 and -10, but later I can modify them. So here we go. I put it there and I okay that. So as soon as I change the gain, now my phase margin is at 43, but still that's not above 50 or 60 that I want. And these are the poles and the 0. That's the pole of the lead. This is the 0 of the lead. Okay, and I can move them if I want to. These are the locations here if you want. You can move them here. So here I can grab one of these and just move it. And look at what happens to the phase margin. You see here, clearly this guy moves, and your phase margin is now 48. If you want, you can further drag it down. Now you see you are at 53. Even if you want to go more than that, let's go to 60. That I initially was shooting for, right? I want the bigger than 60 phase margin, something like this. See, there we go, right? I can go back a little bit, but that's enough. There we go. So more than 60 degrees, infinite gain. This is my root locus. This is my step response. And whether this step response is good or not, okay, you can judge. So here you can right click and go to design requirements, right? And you can add that, or you can go to characteristic and say, hey, show me, for instance, the settling time. I want to see how much my settling time is. Okay, it's less than 1 second, and maybe that's good. In this case, remember, all I was focusing was on the gain margin, phase margin, which is relative stability, and a steady state error for ramp. But here, maybe I can focus on some extra thing, right? Another thing I can add, hey, show me the percent overshoot, right? Let's see if it shows me that. Peak response. Yeah, it doesn't show really the percent overshoots. If you put your mouse over that, it does. So it's 6% overshoot. If this is satisfying to you, you can export it. If not, you can move those zeros and poles again, and you can change it. You can change the gain back. You can go back and say edit compensator, and you can change that gain. If you don't like that gain, you can change it as well. Okay, so you can change that gain. And so here, those 2 points in red and red circle and red cross are the points that you can modify the compensator. So let's say this is what I want. My editor is good. You can add more plots if you want. You can go to the new plot and you can add anything else. Hey, I want to modify Nyquist plot. I want to modify Bode, an impulse response or anything. And there are different ways for tuning as well. But here, the one that I showed you is one of the simplest one. So now you go to, and this is your controller's G, correct? So look here, your G is the plant, and your C is the controller. This is what you tune for. And if you want, you can export it out. So you go to export and say, I want to export it either to MATLAB or I want to create Simulink blocks for them. So right now, I just want to export it to MATLAB. And it says, what is it that you want? I say, I want C, export it, export anyway, and get out. And now if you go to MATLAB and just type in C, there we go. That is your compensator. Now, this is not exactly the one I made, right? Because it's not a unique solution, but clearly this one also satisfies some requirement, and this one gives me a lot bigger phase margin. Okay, so this is what you have. And this is how you do it in MATLAB. So this first part, hopefully you got it. Now let's go to the second part. In the second part, we want to design a PID controller now, where the PID controller is this. I assume the system has, the signals of the system do not have noise, so I don't need to add a filter for the derivative. You know, we typically don't directly do a derivative. Instead, we use a high-pass filter. So we use something like KDS over, for instance, 1 plus n times s or something, okay? And we can make it a high-pass filter as opposed to direct derivative. So this portion does a low-pass filter for me and removes the noise out of the signal. Then I do take a derivative, okay? So I can do that as well if my system has noisy signal. In this case, I assume it's just pure simulation. I don't have noise, so I just go with the original format of PID, not PIDF. And with this controller and with this G, I want to achieve 3 goals. Settling time below 1.5, overshoot below 5%, steady state error to ramp below 0.1. And again, in this case, this is my controller C, this is the plant G. They are in series, and this is your system with H of 1. Yes? So why ramp? Because this system is type 0 system. And type 0, if you give it ramp, the steady state error will be infinite. So why ramp? Because when you add the controller has a pole at 0. So if you simplify this portion or take a common denominator, this is going to be S over Ki plus Kps plus Kds squared. And now if I multiply that by this one, I will get this s multiplied by that. So now the two of these together, my g times c is going to be a type 1 system. And a type 1 system will have a limited, finite error in response to ramp. And if you remember, it was 1 over kV from the previous example. And this kV here is basically the limit of s times c times g as s goes to 0. And if you, what would you get? So that s here, let me clean up a little bit. That s here is going to be canceled with this one. For g, at s of 0, you get 1 over 5. For this one, you get ki. So you get ki over 5. So this guy is going to be ki over 5. And this should be less than equal or less than or equal 0.1. And here, for simplicity, I pick 0.1. And 1 over ki over 5 is going to be 5 over ki. So 5 over ki should be like 0.1, or as I said, less than or equal 0.1. That means your ki should be bigger than or equal basically 50, correct? So if ki is bigger than or equal 50, your error condition will be satisfied. Now, how would you go about those two other characteristics, settling time and overshoot? Well, you know, for settling time, if I use the 2% criterion, that this is 4 over zeta omega n, and here by zeta omega n, I'm talking about the dominance poles. Your closed loop system in this case, which is gc over 1 plus gc, right? Use closed loop transfer function. This is going to be a third order system because C has 1 pole, G has 2 poles, so you're going to get basically 3 poles. So it's a third order system. You have 3 poles, but we can consider 2 of them to be dominant and pick one of them so that it is way down the real axis on the negative side, and it's a non-dominance pole. And that's what we're going to do in a second. By the way, speaking of which, this closed loop transfer function, if I plug this G and this C and simplify, it is going to be basically this numerator of let me see, that should be Ki plus Kps plus Kds squared divided by the product of the denominators plus the product of numerators, which is basically all of that guy that you can see right now in the numerator. So clearly you see it has s cubed, it has 3 poles, but again, for the 2 dominant ones, if we have a zeta and omega n for them, then 4 over that is the settling time, and we want this to be less than or equal 1.5 seconds. Therefore, your zeta omega n should be bigger than or equal 2.67. Okay, and then your overshoot percentage is 5%, so the overshoot itself is 0.05, and this is equal to e to the negative pi times zeta divided by square root of 1 minus zeta squared. And this is zeta. and this has to be less than this. If here you solve for zeta, your zeta should be bigger than or equal 0.7. So here you can pick one zeta, one omega n, and for simplicity, I pick zeta of 0.7 and plug it up here, and I use the equality version of that, and your omega n will be 4. It's not going to be 4, it's actually going to be 3.81. Or bigger than or equal that, but to make it round, I pick omega n of 4. So these are the numbers that I pick. If that's the case, then the quadratic term corresponding to these will be, remember, it's s squared plus 2 zeta omega ns plus omega n squared. So it is going to be s squared plus 5.6 times s plus 16. So this is my quadratic term. Now, as I said, there is a third pole, and that pole is not the dominant pole. So your characteristic polynomial, which is this, should be this guy, but multiplied by the third term, which is s plus that p3 or s3 if you want to call it. So this s3 is your pole that is non-dominant, and then these two should be the same. They should be equal. They should be equivalent. The only question is, what do I pick for this third pole? So anything that makes it non-dominant. Well, if you look at the real part of these two dominant ones, they are at 2.67, right? The poles are at negative zeta omega n. So the real part is 2.67. For it to be non-dominant, this guy in magnitude has to be at least 10 times bigger than this. So this thing should be something like, for instance, 30 or so, or negative 30. In this case, positive 30. So it goes to the other side, becomes negative 30. So if it's more than 10 times bigger than that, that could be a good non-dominant pole, and I can pick that. If that's the case, then I set these two equal. So this guy is going to be a cubic term. This guy is going to be a cubic term. I set them equal. So this one is going to be s cubed plus s squared times basically kd, and then plus 4, and then plus s times kp plus 5, and plus ki. And this one, if you simplify it with 30, it is going to be s cubed plus s squared times, so there will be a 5.6 and a 30, so 35.6, and then s times, there is a linear term 16, there is a 30 times 5.6, which is a big number, right? So that is going to be like 168, 178, 184. And then finally 30 times 16, which is 480. That's 8. So now you say these guys are equal, and from these two, you should be able to solve for the unknown. So the coefficients of the s squared are the same, the coefficients of the s are the same, and the coefficients, the constant, are the same. The cubes are already the same. So you should get 3 equations. The first one is ki equals 480. Now you got the ki, but you have to check whether this ki matches that condition that you initially found. As long as it's bigger than 40, it's good. So you see this condition is satisfied, so you can accept that ki. And then you can look for kp. So kp is going to be basically 179. And then you go for kd, and that is going to be 31.6. There we go. So you found the 3 gains of your PID controller. and this controller should definitely do the job for you. So you can put that controller and define it and put it behind the system and see whether it does the job or not. And I bet it does. Now, let me show you something interesting, and that is to tune a controller, a PID controller for the system, and find this KP, KD, and KI with a MATLAB, with the MATLAB app. Okay, so let me show you that one. So let's go ahead, if I can close this guy. And I do it again here, but this time instead of a lead compensator, I'm gonna do a PID controller. So let's take a look. There we go. Now what I really care about is overshoot, error, and settling time. So I really do not need this part. I can just get rid of it. This is the one that I care about. And the ones that I care about are settling time, and of course when you go over that, the overshoot, right? I guess if you do a peak time, then it shows the overshoot. There we go. So right now it's 30% overshoot, and your settling time is about close to 4 seconds. But I want it to go down to less than 1.5 seconds and less than 5% overshoot. So I need to improve the transient response of the system. At the same time, I need to improve the error to the ramp. Remember, the error to the ramp of original system is infinite. The system has infinite error to the ramp because it's type 0. But by adding a PID, I wanted to be able to bring that infinite down to even 0.1. So I really want to make this system great. How do I do that? Now I go ahead and I say, do I need a new plot? But let's say that's good, what I want. So now I want to go here and I want to tune a PID for it. So let's go ahead and tune a PID. And it says, what is the controller type? You pick PID. And here is where you can add that filter, right? So make it PID plus filter. I don't want it for now. It's good. The design is in the time domain or in the frequency domain. Let's keep it in the time domain. And then what is it that you want? Okay, so here, let me for now just update the compensator, see what happens. And we can go from there. Okay, so here, you see right now, clearly your settling time is very bad, right? The system is very slow. So what I can do, I can make the system quite a bit faster and ask it to update. You see now it came below 1.5 seconds, which is what I want. And what is the overshoot here? The overshoot is 10%. I wanted it to be below 5%. So my overshoot is not good. So let's see if I can change this a little bit. Okay, so now my overshoot increased a little bit, and that is not what I want. So let's see now. 12%. Settling time is bad, so we need to go to the robust side. Still, my overshoot is not good. Maybe I should bring it back here. Make this faster. Okay, now it's even below 1 second. Okay, so this is my current PID controller. But you might say, can I change anything here, right? Can I modify it in this plot? Okay, so if I go here and go to design requirement and say new, let's see if I can specify those numbers directly here. So I say I want my settling time to be 1.5 and I want my overshoot to be what? Let's see. Rise time must be less than that, of course. So rise time of, I don't know, 0.8, settling time of 1.5, and overshoot of 5%. Could you get that to me? Okay, so I okay that and let it do the job. Let's see if it can tune it for me. Okay, so you see it added those requirements for you. This is the rise time, this is the settling time. Right now your settling time is here. Okay, that is your settling time, and these are the locations of the pole and the zero of the system with the PID. Remember, your original system has only two poles, correct, which are at -2 plus minus square root 2, I and j. But now let's see, can I grab any of these and move it? And you see I can. So for instance, if I move this guy, you see that I can basically change the settling time, right? Or I can, for instance, grab this. You see? So right now it brought it into the region that I want, and my overshoot is also in the region, right? Look at that. So I could get both of them inside the regions that I wanted. And once that's the case, I can export it to the workspace, and here it is. I exported it, and look, this is my PID controller, and I can use it with the system and look at the response of it. So that part you can do yourself probably. I don't want to make this video also as long as the previous two videos. So these are the two problems that I did for you: frequency domain design of a compensator and a PID controller in the time domain. And hopefully the combination of this video with the two other videos that I showed you is sufficient for you to review the important things in classic control. Thank you so much for your attention, and I'll see you in the next video.